Hi everyone, this is an optional video that I made for those of you who are particularly interested in seeing step-by-step how you get from the conservation equations that we ended with in the last video to the final version of the equations that includes a turbulent component, which will be revealed in the next video after this one. If you find that this material is not for you, know that you should be able to skip this video without missing any of the key outcomes or concepts that are important for the overall lecture. In order to go from the version of the conservation equations that we have to the final version, there are 3 steps that we need to complete, which unfortunately contain quite a bit of math. The first is to define this rate of change, the derivative that is given a capital D. The second is to then separate each variable into a mean and fluctuating component. The second step is known as Reynolds decomposition. And then finally, the third step is to apply time averaging to reveal the net effect of all of the turbulent fluctuations. And that's what's known as Reynolds averaging. We will start with the definition of this derivative with the capital D. It is known as the material derivative. It's something you may already be familiar with from previous maths units. However, we're still going to go through the definition here today. The material derivative tells you the rate of change in time. However, it is specifically following along the path of a fluid parcel. So if you look at how this arrow is behaving, it's telling you the velocity of the flow as you're moving along the path of the flow itself. If you're in this reference frame from the perspective of an individual fluid parcel moving through the volume, this is what's known as a Lagrangian reference frame. What we would like to do is to convert the material derivative to a simpler frame of reference, which is one that you're probably much more familiar with. This is the Eulerian reference frame. Instead of moving along with the fluid as it's going through the domain, you are going to take a fixed position in space and see how the flow is changing as it moves past that particular point in space. In this reference frame, it is not necessary to follow every single fluid parcel as it's moving through the volume, which makes it much easier to account for the overall behavior of the flow. In the example animation that you just saw on the previous slide, we will now demonstrate what is happening in the Lagrangian and the Eulerian frame. So in the Lagrangian frame, which is the behavior of this arrow on the left, the fluid parcel is changing both its direction and its speed as it is moving along the path through the fluid. However, if you switch to the Eulerian frame of reference, the flow is no longer changing in time at each individual fixed point, but it is changing in space. So as the flow is moving past this arrow, it's changing along the path through that point in space. And so, if you're wanting to convert between Lagrangian and Eulerian, you need to use a definition that considers both of those rates of change. The conversion is given by the equation here. On the left, we have the Lagrangian definition, the rate of change following along the path. The Eulerian equivalent to that considers 2 contributions. The first is how is the flow changing in time if you consider a fixed point in space, and that's what's given by this middle term here. And the second contribution is how is the flow changing in space if you consider a fixed point in time. So now you are considering the change along the path in the sense of both space and time. This definition of the change in space at a fixed point in time depends both on how the flow is changing in space along the path and the direction and speed of a parcel along that particular path. This first component here is equivalent to the flow velocity, so we can turn this vector into something that has 3 components in 3 different directions, given by the u velocity component with a rate of change in the x direction, a v velocity component corresponding to changes in y, and then a w corresponding to changes along the z direction. These 3 terms collectively represent advection. So this is in the exact same manner as what we discussed in one of the previous videos, where the flow is carrying some property of the fluid directly along the path of that flow. and it is corresponding to changes in space along that particular path. If you want to think about this in terms of open channel flow principles, you can consider this first contribution here as a representation of unsteady flow, and the last three contributions as a representation of non-uniform flow as you get a change in space. So in this animation that we saw previously, we have 0 changes in time, because if you fix your position, you see that it doesn't actually change along time, and so this first term would be 0. However, the advection terms representing the change along the path in space would not be 0 in this particular instance. And of course, you can come up with other instances where you might have positive changes in time and 0 advection, or both of them being important. So we can now proceed by updating the conservation equations with the Eulerian definition for this material derivative. What we're going to do for the next several slides is to use the concentration equation as an example, noting that all of these steps in the next few slides are exactly the same for the other equations representing momentum and temperature. So if we replace that material derivative with this rate of change in time and space, we now have a more augmented form of the equation. And this, again, represents changes in time, advection, and as before, the right-hand side of our equation includes other sources that can have direct generation or loss of concentration, and then a net effect of molecular diffusion. Now, what we need to do is take this idea of turbulent fluctuations that you can see in an example time series and correspond it with this augmented version of our equations. In order to do this, we're going to apply something known as Reynolds decomposition. This decomposition separates the signal into 2 separate signals. The first is a mean, time averaged mean component, and the second is the fluctuations and deviations away from that mean value. This decomposition can be applied to any dependent variable that you have, for instance, your velocity, water temperature, and concentration. And what we're going to do is show the vertical velocity as an example corresponding to this sample time series. So in this case, we have the overall instantaneous value at any point in time can be written as a sum of a mean component and a fluctuating component. And looking into this example at the bottom, you have the mean component, and then the fluctuating component at any moment is the distance of the signal away from that mean. We can apply this Reynolds decomposition to the conservation equation, so replace all of the concentrations and all of the velocities and the other terms with a mean and a fluctuating component, based on the definition we gave in the previous slide. And what you get is this even more augmented form of your equation, where your total concentration at any point in time is separated into a signal that only has information about the mean and another signal that only has information about fluctuations from that mean value. And we have the same physical meaning for each of these terms that we had before. This decomposition is only a statistical or mathematical trick. It doesn't actually change the meaning of any of these equations. What we need to do now is expand our equations even further, noting that all of these derivatives of a mean and a fluctuating component can be separated into the derivative of the mean component and a derivative of a fluctuating component. And what you end up with is this even more expanded version of the equation. Now we have a number of different terms. And the next step in our long process is to take the time average of this overall equation. So what we can do is apply a time averaging operator, which is equivalent to putting a bar over all of the variables. And if you apply this operator to the entire formula, it's the same as applying this operator to each individual formula, because these properties commute within the addition terms of the equation. So we can simply say that we're taking the average of each of these individual terms within the equation, as long as you apply it consistently across the entirety of that equation. What we're going to do now, in order to help reduce the complexity of our result, is establish some rules for the outcome of this averaging operator. The first rule is that if you have a constant value or a mean value and you take the average of it, it doesn't change the value. You get back that same mean again. So applying an averaging operator to something that's already constant is not going to change it. An extension of this is that if you apply this averaging operator to a constant value multiplied by a varying value, you can factor out the constant value from the averaging operator because it doesn't change as a result of the averaging operation. So you can take this mean multiplied by the variable that actually varies in time. The next rule is that the order of linear operations can be switched. So integrals and derivatives are both linear operators, and it happens that it doesn't matter which one you do first as long as you do both of them. So if you have the time average of a derivative, it's exactly the same as taking the derivative of a time averaged value. Finally, the last rule is that the average of a fluctuation is equal to 0. So if you separate your signal into a mean component and a fluctuating component, and then you take the mean of that, the mean component is going to be itself, and the fluctuating component must go to 0. Otherwise, it breaks the rules of the Reynolds decomposition that you've established. And just to note here, A and B can represent any variable. So B can actually be the same as A. I'm just indicating that it can also be a separate variable. So you can have, for instance, concentration for A and velocity for B, or you can have concentration for both. Now, what we want to do is apply these rules we've established to help us simplify the equation that we left off with. So for instance, this first term on the right-hand side, we can say that it is equal to capital S net. The averaging operator doesn't change anything. Similarly, you can take this first derivative, the change of the mean in time, bring the average within the derivative using our third rule, and then apply the first rule such that, as with the S net term, this averaging operator doesn't actually change what's inside of it. The main thing that you're going to see as I jump forward one step is that most of these averaging operators are only going to remain over the fluctuating component of the flow, due primarily to this first and second rule that we already saw. So moving forward one step, most of the averages are now only over the fluctuating components, and the mean components no longer have an averaging operator due to the first rule we've established. Now, what we can do is say that any term that is the average of a fluctuation on its own is equal to 0. So all of these terms that are the average of a fluctuating component can be eliminated. The only thing that's remaining are these terms that include a coupling between the velocity fluctuation and the derivative of the concentration fluctuation. So what we get as a result of this Reynolds averaging is a version of the equation shown here, where I've simply removed all of the neglected terms that go away due to our averaging rules. Here is the same exact equation written out horizontally, just to give me a little bit more space with the rest of the slide. And what we have is a version of the equation that has all of the components from the mean quantities. So you have the mean rate of change in time, you have the advection by the mean quantities, and you have the mean effect of everything on the right-hand side. The thing that's new is that you have these additional terms that arise due to turbulent advection. And the reason why you have these additional terms is that this advection is a nonlinear process, and the averaging operation that you conducted has to retain this nonlinear outcome of the turbulent advection due to the averaging rules. To simplify things even further, what we'd like to do now is consider the chain rule. So the chain rule is a property of partial differentiation that allows us to take the derivative of a product of two variables and break it into something that is the derivative of each individual variable in the manner shown in the equation here. What we're going to do now is solve for this term within the chain rule. So you can move this over to the left side of the equation, and it gives you the expression that's shown here on the right. And if we go back to the equations that we had, you'll see that this term here is resembling the terms for turbulent advection that we already have in our equation. So what we're going to do is replace them with what's here on the right-hand side. And what you get is something that for the moment looks a lot more complicated. However, in a few steps, it will actually help us and make our lives a bit simpler. Now, what we can do is group together terms that are alike. For instance, we can move all of the terms that have a leading fluctuation of c to the right-hand side. And what you can actually do is factor out this c term in front of the parentheses and apply the averaging operator to the addition of all of these derivatives. So this is just maintaining some of the same averaging operator rules that we already used. So if we factor out these fluctuations of c, we're left with this expression in terms of the velocity derivatives inside the parentheses. You may recognize that this expression within the parentheses is the same as the continuity equation, which for an incompressible flow is always going to be equal to 0 based on the governing behavior of the flow. So this whole entire term is actually going to be eliminated due to the fact that what's in the parentheses is 0 by continuity. So we can remove that contribution. What you get as a result of this cancellation is the form of the equation that's given here, which, as I noted earlier, you can reach the same result for the other variables. So this is what you get for concentration, but you get the exact same thing by following the exact same process for momentum and for heat. So the resulting equation for those other two variables is now shown here. Each of these involves some sort of a mean varying rate of change component, a turbulent component, an internal source sink term, and then the net effect of molecular diffusion. But what we've done now through the decomposition and the averaging is that we've isolated the net overall effect of all of the turbulent fluctuations into this more compact set of terms that are highlighted here within the box. The final step that we're going to take is to consider only our one-dimensional case where mean quantities are varying only in the z direction. So the turbulent fluctuations instantaneously can vary in x, y, and z, but after you apply time averaging, the time averaged properties cannot vary in x or y in the one-dimensional case. So we're able to neglect any of the terms that are derivatives along x, even the terms that are fluctuating components, because it's the mean or the average of those fluctuating components. The same thing applies to y, so we can get rid of many of those terms. And finally, what we can say is that we don't have any mean vertical flow in this particular instance. What we get as a result of this final simplification is the form of the equation shown here for momentum, concentration, and heat. What you have is a mean change in time component, a turbulent advection component, and then everything on the right-hand side is exactly the same as where we started at the beginning of this exercise. So the only thing that's really changed throughout all of these steps is that we've taken our material derivative, this rate of change in time along the path of the flow, and we've separated it into two contributions. The first is a mean change in time, and the second is this net effect of turbulent fluctuations that arises through nonlinear interactions within the fluid that occur across space.